No, I'm trying to share the screen.
Now we can't see.
Can I?
Yes, I can.
Yes, now I can.
No, I can't.
No, I can. Now I can. That's all right.
Oh, okay.
Can you see it?
Yeah. Yes.
It's beautiful. Then, はじめまして。私はモハです。サウディから来まして。よろしくお願いします。My name is Mohammed Zaki, and I would share a review in the improvement of algorithm estimated L18 carbon ion radiotherapy. So the content will be as shown: introducing carbon ion radiotherapy and few couple of the strategic development. Then preface the topic to look at the method used, the obtained result, and the discussion on the viewed paper. So starting with the introduction, the history of carbon ion radiotherapy began in 1940 when Dr. Robert Wilson proposed the use of fast proton, and then going back to 1956 in the United States, where first treatment of heavy ion began. However,
the slide is not shown. This is not the presentation mode.
Oh.
This is now the editing mode is shown. Can you switch? Yeah. But it's small. Can you?
Now?
Yes, we can see. But can you switch to the presentation mode?
Yes,
presentation
I did.
Slide.
Yes, I did.
You did?
I am doing it now. Now it's in?
But still editing mode.
I am in the presentation mode in my slide, but I don't know.
Oh, really? Can you change, switch?
Make it this mode, editing mode?
I believe you share the editing window.
Wait, let me stop sharing and try to share again. So I share here, screen window, Windows, entire screen. Here. Okay, can we see now?
Same.
Now I put it in the presentation mode. Do you have it in presentation mode?
No, editing mode.
Oh, I don't know.
You push present なんて言うんだろう。これ僕マーカーとか出せないんですか？出せないのか。
Maybe you could try sharing your screen and then enter from their presentation.
Let's try this. Let's try share screen. Then which one should I choose? Entire screen, yeah?
Yeah, try with the screen first.
Okay, let's try this. I'm having the entire screen now.
And go to your and enter a slideshow from there. Yes.
Okay.
Nice. Okay.
Yes. Are we here? Oh, thank you. You are a legend. You're just fixing up my problems. I know. So let's go back again to the presentation. So in 1956, the United States where first treatment of heavy ion began, but it was shut down in 1933. A year later, the first treatment of carbon ion took place on NIRS, Chiba, Japan. Then in 1997, Germany started to treat by carbon ion radiotherapy. It wasn't until 2002 that Japan established to treat on another facility. Then 7 years later, Germany started to treat on HIT. And in 2010, Gunma, using accelerator, Gunma University has started since then an inspiration to increase the number of facility of this very important therapy around the world begin. Currently, the number of facility to treat using carbon ion very limited, and the majority located in Japan. Therefore, there are need to advance it to make it more accessible globally. One strategy to advance it to the world is reducing the accelerator size because it requires massive place to be installed and huge amount of money. Another strategy is to maximize the benefit of the clinical effect. And one way to do that is by improving the algorithm to estimate LAT in carbon ion radiotherapy. So now, quickly prefacing the topic, carbon ion radiotherapy has many advantages over other therapies regarding dose conformity and cell killing effect because of the high LAT, which cause direct interaction with DNA leading to strand break, ignoring the status of the cell if hypoxic or not. And another advantage is it has a better radiobiological efficiency, RBE. Yet special consideration need to be known when determine RBE value, as it has two models: local effect model used in Germany and microsymmetric kinetic model used in Japan. In addition, RBE rely on many parameters, and also tumor exhibit a wide range of RBE values. So to improve tumor control using clinical outcome of RBE profile is very difficult and challenging because of the large uncertainty for each RBE parameters. So instead, using the high LAT direct analysis and optimization of LAT by introducing mathematical correction model to improve the tumor control is way easier. And this is the approach used on the carbon ion first treatment planning system, TPS, in Chiba, Japan. So the paper, the reviewed paper investigated previous TPS treatment planning system and LAT profiles to improve algorithm to estimate LAT, which will lead to maximize the benefit of using carbon ion radiotherapy. There are two treatment planning systems used by NIRS QST, HiPlan and XUN. Both use the MKM model to determine RBE values, yet there are some complications for determining LAT profiles. HiPlan software used only in QST, while XUN has being used in many facilities, but the software is not capable to display the LAT profile by itself. Therefore, in 2018, QST developed algorithm to estimate LAT by substituting XUN drive RBE value into the formula used in HiPlan to describe the relationship between LAT and RBE. Then in the direction of beam depth, different approximation functions were applied to spread out Bragg peak and non-spread out Bragg peak to determine the LAT profile. This original algorithm was not verified by facility using XUN rather than QST. So LAT estimation algorithm was developed by modifying the original algorithm used in QST. The modified algorithm used a quadratic approximation function to estimate LAT on the distal end of the spread out Bragg peak instead of the linear approximation function. LAT estimation algorithm determined the spread out Bragg peak and non-spread out Bragg peak over and overkill region, then apply approximation function corresponding to each region. That's how we can obtain LAT profile. So to determine the LAT profile, the spread out region and calculating RBE value can be achieved by dividing the clinical dose by the physical dose and considering the registered threshold of RBE value for each facilities, such as the table here showing RBE threshold value on Gunma Heavy Iron Medical Center with width of M is representing the width and E over A is representing the kinetic energy per nuclear. And here is the change of RBE threshold value in the overkill region and Lacheria region are plotted for different kinetic energy per nuclear, 290, 380, 400. With the different spread out Bragg peak width from 3 centimeters as minimum and 12 centimeters as maximum. As shown in the figure of each kinetic energy per nuclear, RBE threshold value in the overkill region decrease as M increase. Therefore, the discrimination of overkill region from the Lacheria region by using RBE threshold become most difficult at maximum 12 centimeters maximum width. From this, the change in RBE with depth is shown steeper in the overkill region, and it is unlikely to determine the overkill region using only RBE because it does not increase exponentially, and the change is very steep in the overkill region. Therefore, the overkill region can be determined by adding the range of the physical dose in the LET. So to improve algorithm, authors look across LET estimation for the overkill region and non-overkill region. Consequently, for no determinant of spread out Bragg peak, linear function approximation applied into the non-spread out Bragg peak region. For determining spread out Bragg peak without the overkill region, also linear functional approximation applied into the spread out Bragg peak region. And for determining the spread out Bragg peak with determinant of the overkill region, quadratic function approximation was applied into the overkill region, and the result was also used to verify algorithm performance, in addition to provide an assessment of LET distribution with LET volume histogram too. Also to provide a clinical pipeline for LET assessment using TPS and Python to improve algorithm for LET. So result, figures here show the feasibility test for the original LET estimation algorithm on Python platform. We can see here on the first and the second result, the LET distribution for a single beam along the central axis in water using both high plan and XUN as a reference from QST along the central for kinetic energy of 350 and 350 with width of 6 centimeters. Here an illustration of the estimated LET diffusion from the reference for a given range of the spread out Bragg peak is shown. And here result an illustration of the overkill region for 350 MeV with various spread out Bragg peak width M1, M3 until M12. The LET estimated for both XUN and high plan showed massive agreement with the original LET, which indicate that the LET estimation algorithm runs with the high accuracy on Python platform. For that, modified algorithm used the same platform. The feasibility test revealed that the diffusion of the estimated LET from the high plan was greater near the distal end of the spread out Bragg peak than the original. This was recognized as the overkill effect, which make linear approximation of the LET based on the RBE for this region very complicated. So to overcome this, a quadratic function was introduced to approximate the relationship between LET and RBE in a high plan in the overkill region. So using the modified algorithm shows improvement of LAT distribution for the entire length of a single beam along the central axis in water with the same width and the same kinetic energy per nucleus. Here, using a modified algorithm, we can see the diffusion. The diffusion of the estimated LAT from the reference in the overkill region becomes significantly smaller, from 28.1 plus or minus 21.7 to 1.5 plus or minus 1.3. And this is a huge achievement for the modified algorithm. Therefore, improving the LAT estimation performance for the overkill region by 80% has been achieved with the reference across various of spread out Bragg-Peak width. Here, on the third result, it shows LAT estimation using facility-specific RBE threshold value. Distribution of LAT for a single beam with kinetic energy per nucleus of 290 MeV with width 3 centimeters. And for this single beam, the analysis revealed an unexpected slope in the estimated LAT at the proximal end of spread out Bragg-Peak, which was mostly obvious in this case, where 219 kinetic energy per nucleus is the value, and with width of m equal to 3. Detailed inspection revealed that the RBE threshold value registered in the XUN system are highly different between QST and Gunma Heavy Ion Medical Center. And that might be the reason which caused this slope. Later then, to inspect the validity of the modified LAT estimation algorithm in Gunma Heavy Ion Medical Center, XUN, they ran it using Monte Carlo simulation to provide the LAT profile as a reference. The single beam of the 380 with width of 6 centimeters revealed that the estimated LAT showed fair agreement with the reference value. The diffusion of the estimated LAT from the Monte Carlo simulation derived in the spread out Bragg-Peak region was 2.3% plus or minus 0.67%, supporting Gunma Heavy Ion Medical Center facility specific LAT for this modified algorithm. So discussion, the estimation error for the overkill region on the original method LAT, to estimate LAT with a linear approximation, was as large as 28.1 plus or minus 21.7, where the method proposed here by using quadratic approximation for the overkill region improved the estimation error to 1.5 plus or minus 1.3. And this is a huge achievement. So therefore, the modified algorithm become more beneficial for estimating LAT in those regions. Because the approximation formula are based on the approximation of high plan data, the LAT estimation error at Gunma Heavy Ion Medical Center was 2.3% plus or minus 0.67% when compared that to the estimated by the Monte Carlo simulation, in which the error appeared mostly near the overkill region. This error could be reduced through modifying the approximation formulas to match the facility-specific Monte Carlo result and data. The results of this reviewed paper suggest that it is necessary to use a facility-specific RBE threshold value to distinguish the spread-out Bragg-Peak, non-spread-out Bragg-Peak, and the overkill region with respect to other parameters. because application of a threshold specific to a given facility to dataset from other facilities would result in an LAT estimation error. Yet, when LAT distribution is the same with the same energy and spread out Bragg peak size, the same set of approximation formula could be used for RBE to LAT conversion, regardless of the place of carbon ion radiotherapy, where it's located. Limitation of this study is that the proposed method is applied only to beams in the vertical or horizontal direction. The method is not compatible with plans involving a rotating gantry. For such cases, algorithm need to be revised. So to conclude, new approximation function for LAT versus RBE were developed for the overkill region. Better estimation accuracy can be made using the developed algorithm to estimate LAT of XAUN in carbon ion radiotherapy plans. The performance of the algorithm was validated in multiple facilities. Applying modified LAT estimation algorithm to previous dataset to visualize distribution and LAT volume histogram in multiple model cases was achieved. LAT estimation performance was examined at two facilities using Archifel and Monte Carlo simulation respectively as a reference for RBE. Results are expected to become incredibly valuable to help making carbon ion radiotherapy more accessible and advancing it to the world. The findings of this research study have significant implication for the field of carbon ion radiotherapy treatment planning and highlight several potential future research topics. And here where I finish the review, happy to hear any of your comments or to answer any of your questions. Arigatou gozaimasu.
Thank you for your presentation.
Thank you. Arigatou.
Then we will start question and answer and question session. Are there any question or comment from master student? If not, are there any question or comment from all?
I think I stopped sharing. Yeah, I stopped sharing, so thank you. Arigatou gozaimasu.
いいのか。じゃあ、OK, thank you.
Thank you.
じゃあ、this meeting is finished.
はい。
Thank you.
お疲れ様でした。